Hello, good morning, good afternoon, or good night, everyone. Don't know where you guys are located, but hello to everyone. Welcome to the first Data Science Summer School organized by Hertie School Data Science Lab and Data and Methodology Center of the Scripts Cluster of Excellence. I would like to thank our funders, the Scripts and the Stifterverband, for their generous support that actually made the summer school happen. And I'm extremely happy to see you all here today, both on Zoom and on the parallel stream on YouTube. I would like to note a couple of the organizational and technical details. If you're in the Zoom meeting, you're all muted and you have your cameras off upon entrance. Please do not unmute yourself and do not turn your videos on unless you have a question. We really ask you to put the questions in the chat. That way it's going to be easier to handle the questions for the TAs and for our instructor. And if you really want to speak up, then please raise your hand and then we will give you a moment to speak and to ask your question. Then you will be able to unmute yourself and turn your camera on if you want and to ask a question kind of live. But again, it's really great. It would be really great if you can leave a question in the chat anyways. If you're on the Zoom, if you're on the YouTube session, you can leave your comments and questions in the live chat. We will try to handle the questions as fast as we can, or we will direct the questions to the instructor and the TA as well. I should also remind you all that the Zoom session is being recorded, and I'm thanking you all in advance for following these rules. And we shall begin with the 8th workshop on this summer school workshop series. And today we have research design and causal analysis in R. And let me introduce you Dr. Julian Schuessler. He's a postdoctoral researcher at the Department of Political Science in Aarhus University in Denmark. His research focuses on causal inference and statistical problems, including instrumental variables, missing data, and power analysis for survey experiments, as well as public opinion in the European Union. Julian, the floor is yours. You can share your screen now, and thanks so much, everyone.
Hello, and good morning, and good day, and good night also from me to everyone. It's great to see so many people here. And thanks to Olga and the organizers and to Hertie School for inviting me. And let me share my screen. Oh, I cannot share my screen. Sorry, Olga, because I accidentally logged off like a minute ago and re-entered the chat. So I think you have to give me co-host rights again. So I guess I have to wait.
1 second. Yeah, it's the
yeah, I think I've got it. So I think you should see my screen now. Beautiful.
Yeah, perfect.
I wasn't sure what I was expecting because I was expecting a number of participants somewhere between 200 and 1,700. So let's see how big the interaction part is going. You should have received some version of the slides perhaps yesterday. I've updated them quite a bit. You will receive them after the session, the latest. You should also have received a link to Colab, where you can work with R in your browser if you do not work with R on your computer. But let me perhaps start again with me. So I'm a postdoc. My background is political science. I'm at Aarhus in Denmark. As Olga just said, use the chat or raise your hands if you have any questions in between. We'll try to have a lunch break at around 12:15. Expect lots of polls. So I'm going to try to use a lot of polling. I have like 7 or 8 questions for you at various times. So be alert. And it also pays off to have pen and paper ready. And as I said, we're going to use some R, some very basic R. And so you can either use your own R Studio, or you can use Colab, for which you should have received the link. And most of the code is already in Colab. So actually, if you're using your own RStudio, it makes sense to still open that link to Colab, because then you can just quickly copy some of the code from there. And if you're using Colab now is also a good time to run the first code snippet, which just installs some packages. And that's going to take like 5 minutes. So it probably makes sense to just run that part now and then just wait and have it run in the background. Right. Oops. I have a pretty ambitious program, I think. Let's see how that goes. We have 80 participants in Zoom right now, so I have no idea about your backgrounds. I've seen some familiar names. Some people I think I know from Twitter. So I think we mostly have a social science crowd. But what I'll try to do is I'll try to start fairly slowly and then accelerate throughout the 4 hours. And I guess we'll just see how it goes and how far we get and how many questions you have. What I'll start with is I'll talk about control variables, because that is something we encounter all the time. And around control variables, there's a few issues I can discuss using causal graphs. Then I'll talk about linear regression and how to assess sensitivity of your estimates of causal effects using something that is called sensitivity analysis in R. And then that already will take us 2 to 3 hours, I think. And then depending on how fast we're going, I will introduce some basics about mediation analysis and perhaps also talk briefly about instrumental variables. And all of this is going to heavily be based on causal graphs. So I might as well have called this course causal graphs, or DAGs as they're also called. And the other thing that pops up or that I focus on is sensitivity analysis. So I will mostly revolve around these two things. Okay, so that's the approach. Let's start slowly and think about some control variables and what models we should run when we have data. So here's some data that I plotted. There's one x variable on the x-axis. There's an outcome, a dependent variable y that is on the y-axis. Every point is a data point. It's a lot of scattering. It's a lot of noise. And the first question I have for you to answer quickly in a poll that I'll send to you is, what happens when I run a linear regression using these data that are depicted here of y on x? So is it going to be positive or negative or 0 or insignificant? Just like a basic question. And I'll send you the link in just 1 second into the chat. So here's the link to the poll. And sorry, that was the wrong link. Oh my God, that's a bad start. Sorry. So here's the second link should be correct. Yes, so what will the linear relationship between x and y be? Will it be positive, insignificant, or negative? Based just on this picture that you're seeing here. So perhaps take a deep look at the picture and just take a wild guess what the relationship will be. And I'll just wait for a few seconds. Okay, so the first results are coming in. Oh, and I'm using again the wrong. Sorry, that's not working how expected. Sorry, guys, just give me 1 second because I mixed up those. Okay. Nice. So we have 58 votes, and we have a clear majority that says the relationship is 0 or at least insignificant, and that's a very understandable opinion. It's actually not true. So if you run the regression of y on x, you actually see a tiny, slight positive relationship that is actually highly significant because the data is 1,000 observations, but I admit that is very hard to see. So perhaps this is also a lesson on how hard it sometimes is to interpret plots and to see relationships when there is a lot of data. And just to make sure that everyone is on the same page, so in R, you would use the LM function, declare the dependent variable, and use the tilde sign, then declare the independent variable. And then if you want, you can also apply the summary function to that output. And then you'll get a few results. And to summarize these in a table, the regression coefficient is estimated to be like 0.1, which again is very small, but it's highly significant on the 1% level because the data set is in fact quite large. So that's, I hope, is not terribly exciting for most of you. That's just a simple linear regression that we've ran. So it turns out that I forgot something. Well, first of all, here's the regression line. If you plot it, so it's not very steep, as you can see. It's a very weak relationship, but it's there and it's positive. Now, what I forgot is there's actually like an additional variable in the data set that I called U. And U is just a binary variable, so it's either 0 or 1. And this here is the same plot as previously, but I just colored in the values of this third variable U. So all the black dots have U equals 0, and all the red dots have U equal 1. And so the question is, what happens if we include this U variable in our linear regression? And to answer that problem, I have a second question for you, which is, we have this variable U, so is it correlated with our independent variable, and is it correlated with our dependent variable? So, and again, I have a poll, and I hope this link should be correct. Yes, it is. So I'll send you the link in the chat. And so just take a second. And Olga just asked sound quality. Let me try different. What do you mean by echo, Olga?
I think we can just hear an echo.
Echo.
It's possible that you're maybe like moving away from the mic, and the room is big. I don't know. Maybe if it's possible, you can try headphones. Maybe I don't know.
I've now switched my microphone. Is it better now?
I think this is better.
Test. Blah blah blah.
Yeah, I think this is better. Yes.
Okay,
yes,
I see people writing in the chat. Okay, so thanks for the feedback, and I'm glad I could solve it. Yeah, so is U correlated with X or Y? Let's see. Let's have a look at the results. Okay, so that's not as clear, but there's a slight majority that says that U is correlated with both X and Y. Some say it's only correlated with X, some say it's only correlated with Y, some say it's uncorrelated. But it's, yeah, so we're approaching 50% saying that it's correlated with both. And
Julian, you're not sharing your screen, just to make sure that.
Sorry. Yeah. Here we go. So the answer is it's correlated with both. So it's correlated with X because the red points are all on the right side of the plot, basically. So if your X value is high, you're much more likely to have U equals 1 instead of U equals 0. So it seems that U and X are positively correlated. And then the correlation with Y is a bit harder to see. But here again, we have a positive relationship. You perhaps see that all those high values up here, the high values of Y are also U equals 1. So there's also a positive relationship between U and Y. And so the next question then, of course, would be, what happens if I include U in the linear regression? So does it change anything about the relationship between X and Y? And here again, let's do just a quick poll what the relationship will be between X and Y if you control for U. Just take a second and think about it. First votes are coming in. So again, use positively correlated with both X and Y. Okay, I think most people have voted and we have a very slight majority. Oh yeah, so it's torn between 0 relationship and negative relationship between X and Y. Although also quite a few people say that it would be positive. So it's kind of unclear, I guess, it's kind of hard to tell. But if you perhaps look at the graph and imagine fitting 2 separate lines, one just among the black dots and one separate line just among the red dots, you could perhaps imagine that the relationship would be negative. And this is actually what is happening. So the original regression, remember, was just a weak positive relationship. And then if I just add the U into the linear regression, what actually happens is that the regression coefficient for X switches its sign. So it was 0.1 positive. When I control for U, it's actually minus 0.3. So that's a pretty drastic difference. And I just hope that is not news for everyone. Here I have it visualized. So what I did here is I actually drew separate regression lines for those 2 groups, U equals 0, U equals 1, which of course is one way to control for U, like to split the data depending on the value of U, and you see a negative relationship between Y and X. So this phenomenon where dependencies or correlations between 2 variables switch around when you control for additional variables is actually kind of famous, and it's called Simpson's paradox. It's not really a paradox in the mathematical sense because it's a fairly simple fact about data and about probability. But I think it's called paradox because it often surprises people, because I think humans have an intuition that once you have a relationship, it's supposed to be stable, no matter how you slice the data and no matter what you additionally include. But I guess if you've ever worked with real data, you are well accustomed to this paradox where relationships vanish or switch around or become much smaller or much larger, depending on which variables you include in your statistical model. Okay, so that was mostly thought as a recap of some basic regression, some basic data plotting, some basic R. The data are not real. So what I did was I actually simulated some data, which I think is a very useful thing to do. This is the R code that is also in the Colab. And perhaps let me just briefly explain what is going on here. This code generates three variables that are called U and X and Y. U is a binomial variable of size 1, which means it's a 0, 1 variable. It's 1,000 of these, and the probability parameter tells us that it's 50-50, 0 and 1. And then R stores this in a vector of size 1,000. X is a function of U, so it depends on U. You could also say it's influenced by U, plus some noise that is uniformly distributed, which doesn't matter that much. And then Y is a function both of X and of U, and some additional Gaussian or normally distributed noise, all of which has 1,000 observations. And then you get three vectors, U and X and Y, that each has 1,000 entries. And then you can use this directly in R and run these regressions that I've just shown to you. Okay. Perhaps the more interesting question is, how again is it that these results differ depending on whether I control for U or not? And then perhaps you remember from basic statistics that if you compare two regressions, so this first equation here is the first regression where it's just Y and X, and there's an intercept, there's a coefficient on X, there's a residual. All of these have res subscripts for restricted, because in some sense, this is a restricted model. And then the extended model, the extended linear regression that also includes U, is the second equation where you control for U and there's a coefficient C on it. And these two regressions I just showed to you, the first one gave a positive relationship, the second one gave a negative relationship. And now perhaps you remember, or perhaps you know, that there's some basic formula that explain why the B's would differ between these two approaches. And the difference turns out to be this expression here, which consists of C, which is just the regression coefficient for U when controlling for X. So C is just that regression coefficient. And then this more complicated looking thing you could call imbalance, and describes the relationship between X and this third variable U. Specifically, it's the regression coefficient when you regress U on X. So that means that the difference between those two regression coefficients depends on the relationship between U and X and between U and Y controlling for X. And one way to remember this formula or this phenomenon is the phrase impact times imbalance. So impact would be C, that's the impact of this third variable U. And imbalance is this more complicated thing, which describes the relationship between X, our independent variable, and U. A more traditional name for this is omitted variable bias, although there are a few problems with this phrase that we'll see and explore now, because bias here is a very imprecise term.
Wow.
I can hear someone talking.
Sorry about that. We muted the person.
Yeah. So that's the omitted variable bias formula, or the impact times imbalance equation. But the question is, so which regression is correct? They give totally different answers. In the first case, the relationship between y and x was positive. In the second case, it was negative. So when we measure u, we can choose between those two, and we have to choose because they give conflicting answers. So the question is like the first regression biased and we should control for u, or is it the other way around? And how are we supposed to think about this issue? And now here again, I have a poll, so I'll send you the link in just 1 second into the chat. Here it comes. Take a second to think about it. Which regression is correct? The one without you, the one with you, or does it depend on something? Or maybe you just don't know, which is also a perfectly valid answer. Okay, and that's pretty quick. People are still voting. Okay, I think we get a pretty clear majority of about 70% that says it depends, although that is always a safe answer. 20% say that you should control for u, which I also think is a very understandable answer, because that is certainly what I would have said until a few years ago, just from my basic statistical education. Yes, we have about 1/4 saying you should control for u, and a few people are honest and say, I don't know. But the correct answer indeed is it depends. But the more interesting question then is, of course, it depends on what. And it depends mostly on two things. It depends on the substantive question we are asking, and it depends on the assumptions we are willing to make. And so let's talk about questions first, and then we'll talk about assumptions, all based on causal graphs, if there aren't any immediate questions on this stuff, which I guess is not the case. Cool. So I'll do this through an example, which is a survey data that comes from Sudan, from Darfur, where there was a lot of mass violence in the early 2000s, killing a lot of people that led to indictments of genocide and other crimes in the International Criminal Court. And one thing you can ask about this situation, but also about other situations where there is unfortunate violence is, so does violence lead to more violence? Does violence beget violence? Or perhaps does individual experience of violence lead people to demand peace? So these are two things that you could imagine that occur when people suffer from violence. And in perhaps more precise terms, you could ask, what is the causal effect of experiencing violence on how you think about or what you demand, whether you want revenge or you want peace? And that is a question that Chad Hazlett asked, and he did a survey in Sudan and analyzed the data. So I hope that's a fairly straightforward question. And you could visualize it with a very simple causal graph. So this is a first very simple causal graph where the variable d, or the node d, just depicts whether an individual experienced violence and said so in a survey to a researcher. And then y is just measures about how this individual thinks about violence and peace, whether the individual think you should make peace with the enemy or whether you should not, for example. And of course, this causal graph just depicts our hypothesis that whether you experienced violence may potentially affect how you think about peace and violence in Sudan. A perhaps more realistic graph for this setup, for this study, includes other variables, because seems very implausible to just assume that it's just violence and what you think about it that matters. And indeed, Hazlitt in this article argues that violence was driven or was targeted based on the gender of persons and where they lived. And so here in this graph, X stands for at least two variables, in our case, gender and where a person, in which village a person lived. And the story here is, of course, that the gender and the location of a person potentially impacted on whether that person actually experienced violence or was harmed or not. And perhaps through other channels, these two variables also affect what that person thinks about peace and violence and how it thinks about the enemy in that civil war or war. So based on this alone, you can ask a bunch of questions. So the motivational question that I presented to you was, okay, so what's the effect of violence and attitudes? And that's the question that Hazlitt tries to answer. But you could also ask other questions. You could ask, so what's the correlation between violence, between experiencing violence and what you think about violence? That is a non-causal question. That's just a descriptive question. How do these two things correlate or depend on each other? And there's even more. You could also ask, what is the correlation between those two variables when you control or condition on or given the same gender? Which again is a non-causal question, because basically that is just a regression that you could run and you will get an immediate answer. And the regression will tell you that answer. And it's a different question from asking what is the causal effect of violence and attitudes among, say, women, which is sometimes called a conditional effect or subgroup effect. And lastly, perhaps you could also ask, what is the effect of gender on attitudes through experiencing violence, which is an indirect effect. So that's related to causal mediation, which is something that we'll probably talk about later. So there's a bunch of questions you can ask, and for now, we'll mostly focus on the very first one and on understanding how it differs and how the answer differs from between the first question and the second, perhaps also the third question. These were the questions, and there's not much more due to time constraints that I can say about that. I also presented to you two causal graphs, or more specifically, directed acyclic graphs. The abbreviation is DAGs. Just really quickly, they're called directed because every connection between two variables or nodes has a direction. So it has a clear arrow that goes in one or the other direction. There is no simple lines and there's no arrows going both ways. And these two graphs were acyclic, which means there are no cycles in the graph. So no mutual causality and no feedback loops. And just a tiny bit on the history. So these were first used by a biologist called Schuessler Wright in the 1920s, then became very popular in the 60s to 80s in what is now called structural equation modeling, and have researched and used mostly due to work by a computer scientist called Julian since the mid-90s, and are nowadays a very popular framework for working with causality in many disciplines, including machine learning, artificial intelligence, statistics, sociology, and also my discipline, political science. And I think they're extremely useful. And so I'll try to concentrate quite heavily on how we can work with these graphs to get a better understanding about on causality and statistical modeling. Fundamentally, I hope it's obvious that causal DAGs or causal graphs visualize causal assumptions, just as I just described, about, for example, how gender impacts on whether you experience violence or what you think about violence. It is very important to remember that the important assumptions are the arrows that are left out from the graph, so the arrows that are absent. Because if there is an arrow that is absent between two variables or two nodes, then we are communicating the assumption that this corresponding causal effect definitely does not exist. On the other hand, if we draw an arrow, for example, between experiencing violence and what you think, your attitudes towards peace, then we are just communicating that we think there could be a causal effect. We are not necessarily committing us or saying that it definitely exists. We are just saying that it could exist, and that perhaps we want to determine its direction or its strength. So the important assumptions are those that are left out. This is very important to remember, and we will return to this. And now, generally speaking, of course, if your assumptions are not true, or are very much not true, or are really bad, then it is most likely that the results you get from anything you do are also wrong or bad. And on the other hand, if your assumptions are at least approximately correct, you can have some confidence that your results are also going to be approximately correct. And in general, causal inference without assumptions is simply impossible. And the only question is, how explicit are we about the assumptions? How easy are they to understand? And are they plausible or not? Okay, so if there aren't any questions, let me perhaps show you just the basic results from that study on experiencing violence and what you think about peace. This here is a graph that shows point estimates. Those are the black circles and the black triangles, plus confidence intervals, which are the gray lines. And one important thing I've marked with a red square rectangle is that if you do simple OLS regressions like I did 20 minutes ago, of whether a person says that you should make peace with former enemies on whether that person has experienced violence, you get a positive estimate that is around 0.1. So if a person has experienced violence in the past, that person is 10 percentage points more likely to say that you should make peace with former enemies. That is a correlation that we could interpret causally. And then that would mean, if we interpret it causally, that experiencing violence leads persons to demand more peace. So then it would seem that it is not true that violence begets violence, which I guess is a broadly positive result. And what this picture also tells us is that these 2 point estimates and confidence intervals are pretty much the same, no matter whether the regression is short or long, where short just means a limited set of control variables, and long means more control variables. So that relates to this question of whether you should control for third variables or not. In this case, it barely makes a difference. Okay. There's one question in the chat. Yes, that's a good question. So there's a good question from YouTube that asks, is there a temptation to have loads of arrows to avoid missing any possible causal relationships? So that relates to the point I just made. about that the important assumptions, the strong assumptions, are the errors that are left out. So of course, if you want to be safe, assumption-wise, you could just include all the errors that exist there. The cost to that is, if you think in the extreme case that everything affects everything else, then you cannot learn anything about causality by just observing data. So the overarching thing that we're trying to do in social science, but also in other sciences, is we usually have some data that is not perfectly experimental, that is observational, that is observed. And then we have to make some assumptions. We have to rule out some errors in order to make some progress on learning about causality in the absence of experimentation. And so if you honestly think that everything affects everything else, then there is nothing you can learn from the data about causality because everything is just hopelessly contaminated. So that's a very good question, and perhaps that answers the question. There's a second question that I think I'll answer in a few minutes anyways. All right, so just to have a quick interim summary, we've seen that controlling for third variables can make a huge difference in this simulated data that I showed to you, where I controlled for U or not, and the sign of the regression coefficient switched around. I've quickly mentioned the fact that you can ask causal questions or non-causal questions when you have some data. And I've shown you some basic DAGs. And now, of course, the question is, so given that I have a causal graph, a DAG, and that I want to estimate, for example, the effect of violence on attitudes, how can this DAG tell me whether I should control for a variable or not? Because as we've seen in the beginning, that often can make a very significant difference. And so we have to be very, very careful about whether we control for a variable or not. And so that's the second part. So again, we're interested in the causal effect of violence on attitudes. We have some additional measured variables where we think about whether we should perhaps control for them in our statistical model. It doesn't matter whether it's a linear model or some non-linear, more complicated thing like a logit or even some fancy machine learning stuff. And we could think about a rule that tells us whether to include X in our statistical model as a control variable. And in the ideal case, the rule has two properties. First, the rule tells you you must control for this variable, you must control for that variable. And secondly, it never tells you to control for a variable that actually produces some problems. Okay, so that would be, these are two requirements that a good rule needs to fulfill in order to give us valid answers. And so what I have for you now is a few example rules that you perhaps have seen in the past and that perhaps are good rules or not. So you could say that you should control for additional variables if that variable is associated with the outcome. That sounds sensible. Or you should control for something whenever it's associated with the independent variable. Or, of course, only if it's associated with both the independent and the dependent variable. A more intricate formulation says you should control for variables that are associated with independent and dependent variable that are unaffected by the independent variable. You may think about controlling for stuff that affects the outcome. And the last two ones are more technical. You may want to control for variables where it holds that conditional on these variables. So this funny sign means given the other variables x, d and y are independent or uncorrelated. That could be yet another rule. And the last rule would be that conditional on the other variables, the independent variable is independent from the potential outcome of the dependent variable with respect to the independent variable, which, if you don't understand that, that is perfectly understandable. That's kind of the point why I'm saying it right now. So that's 1, 2, 3, 4, 5, 6, 7 rules that more or less conflict with each other. And so I have another poll for you where you can cast a vote on what you think the good rule is that tells you which variables to control for and which not. So here's the link to the poll. So just take a second to think about it and then cast your vote. Let's see what is happening. Okay, so it's a tied race between the control variables being associated with the independent and the dependent variable, and between that more complicated rule that they are associated with independent and dependent variable, but unaffected by the dependent variable. And Edward has a good question on that. How is it possible for the control variable to be unaffected by D, but associated with D and Y? I think that will become clearer just in perhaps 5 to 10 minutes. Okay, and we have, I think most of the votes are in, and we have a slight majority that says you should control for variables that are associated with the independent variable and the outcome variable, which is also the rule that I learned in my undergrad statistical education. And then we have, so that a third of you says that's a good rule. Another quarter says it's the Koske-Imai rule, unaffected by the independent variable. And then the rest is scattered over the other options. So the answer is all of these rules are bad. All of these rules do not satisfy these two requirements that are formulated, except the very last one. So the last one was perhaps the most complicated one with that potential outcome that I don't think is very intuitive. And the bad news is that all of these other rules, some of which sound pretty plausible, are actually wrong. And there will be occasions where these rules tell you that you should control for a variable and you will make a mistake. Okay, and that's pretty bad because I think these rules, or some of these rules, are kind of folk knowledge or even textbook knowledge. And so many scientists that work with data follow these rules. And unfortunately, they will therefore sometimes make a mistake. And what I'll do now, or what we will do now, is we will use causal graphs to find a rule, yet another rule that is actually pretty easy to understand, and that is a good rule that identifies correctly whether you should control for a variable or not, if you are interested in a causal question. Okay, and that's going to be, I guess, perhaps the thing that is most useful to the most of you in this workshop. And it's not entirely straightforward, but I think it's it's easy to understand if you walk through it slowly. And we have to do one more step before, which is to understand how, if we think that a certain causal graph is correct, how that what this causal graph implies about the correlations or the non-correlations that we see in the data. And once you have understood that problem, then finding such a good rule for choosing control variables is pretty easy. So let's first talk about more broadly about causation and correlation in causal graphs. And that leads us to something that is called D-separation. And the cool thing is that with those directed acyclic graphs, they can be pretty big and lots of arrows and very complicated to read. But at the end of the day, there's just 3 basic graphs or basic structures that you can use to build any more complicated graph. And the first graph is this one here, which is just 3 variables. D influences M, M influences Y, end of story. And now we just ask if this is the graph or if this is some structure that we think that is happening in the real world, do our independent variable and our outcome correlate? And I hope it's clear that they do. So the answer is yes. So for example, if the independent variable positively influences M and M also positively influences Y, then D should positively influence Y, and then D and Y should be positively correlated. The next interesting question is, what happens to the relationship between D and Y when I control for or condition on M? Well, then it vanishes, because controlling for the thing in the middle kind of blocks the information flow between D and Y. Perhaps it's more intuitive to think about, well, one intuition for this is to imagine that water is flowing from left to right along these arrows, and then the water flows. But if you block the middle thing, if you control for M, the water cannot flow, or the information cannot flow from D to Y. And so therefore, you shouldn't see a relationship between D and Y once you control for the thing in the middle. And if you do not believe this, then you can go to the Colab, and there's actually some simulation code, which is hopefully straightforward to understand, where I generated, or where you can generate right now, a variable D that is just 1,000 observations of a standard normal distribution. And then M is a function of D plus some noise. Y is a function of M. Here's a plus sign missing, plus some noise. And then you can run 2 regressions, Y on D. You'll see that there's a negative relationship. And then if you control for M, that relationship between Y and D becomes pretty much 0. So perhaps you can just take a minute and run this real quick, just to make sure we're all on the same page. So I'm assuming that's working for everyone, or I'm assuming that everyone just believes that it's true what I just said. Gulnas just asked in the chat, what about partial mediation? I think we'll get to this. So I think the question is, what if there is an additional arrow from D to Y? Then of course this changes, but right here we're assuming the most simple scenario, just to get a handle on what happens in this most simple scenario. And in a graphical language, we say that we have a path between D and Y that goes through M. A path is a walk that you can take on the graph, starting in one variable, going to the other, to some other variable, and never passing any variable twice. So it's just like a one-way thing. But the direction of the arrows does not necessarily matter, as we'll see in a second. So that's a very simple path here between D and Y. And we say that the path is open in the sense that the path creates a correlation between D and Y because information or water or causation is flowing from D to Y. And so we should see a relationship empirically. So we say the path is open. And as I've just argued, and as you have perhaps confirmed using the simulation, once you control for M or conditional on M, this relationship between D and Y vanishes, and we say that the path is blocked when we condition on or control for M, the variable in the middle. Okay, so that was the first tiny path that you need to understand. The second possibility, of course, is reversing the arrow between M and D. So this is kind of like a fork structure. You could also call this a fork. You could also call this a confounding graph because M impacts on D and Y. And so in a certain sense that we'll make more precise later, M confounds the relationship between D and Y. And I hope that this is something that is perhaps even more intuitive. So we have a variable that impacts on two variables. And I guess we all know that this may create a relationship between D and Y, even though D by assumption in this graph does not affect the outcome or the other way around. So yes, D and Y correlate. What happens when I control for M, if I have data on this, well then again, and I hope that's intuitive, the relationship vanishes. Once I take into account values of M for data points, then given M within the subset with the same M, there should not be any connection between D and Y, and therefore there should also not be any correlation or any other empirical relationship between D and Y. So that means again that this path is open. Once we condition on M, it is blocked. So there is a correlation between D and Y. When we control for M, this correlation should vanish if this is the correct graph. And examples for this are many examples of third variables influencing two other variables. Okay, and so finally, Stefan has a slightly longer question. Okay, so Stefan has a good question, but I think that will lead us a bit astray given the time constraints. So I don't think I'll answer it right now because yeah, that would just lead us astray, but it's a good question. So the first case was this chain of mediation. The second case was the fork. And then the final third case is this one here, where the arrows collide in the middle, if you look at it. And so this is sometimes called a collider path, or you say that the variable M in the middle is a collider because two arrows collide in it. And perhaps it's intuitive, perhaps it is not. But if this is all that is going on with these three variables, causally speaking, then D and Y do not correlate. And I'll give you two concrete examples later. D and Y are just two completely independent things, two independent causes that influence the thing in the middle. And so if you just look at the relationship between D and Y in the data, if you've measured them, then you will see no relationship. But interestingly, it turns out that when you control for M or condition on M, so the node in the middle, then you will actually see a relationship between D and Y. And I'll give you two examples for that in just a second. But that means in graphical terms that the path is blocked if you don't do anything. There's no information flowing from D to Y. However, once you condition on the collider in the middle, it is open. And let me remind you that we have a path between D and Y because we can walk across arrows from D to Y, even though the arrows sometimes go in the one direction, sometimes go in the other direction. But for this concept of a graph, of a path, sorry, that doesn't matter. The path is blocked, conditional on M, it is open. We say that M acts as a collider, and so what is going on here? The first example is the relationship between how clever you are and how good looking you are and how famous you are. So perhaps it is the case, I'm not saying that is actually true, but perhaps it is the case that different people are more or less clever, and perhaps something like the IQ is a good measure or not for that. It doesn't matter for this example, but let's just say some people are cleverer than others or have higher ability in some aspects, and that's the IQ variable. And then those same group of people, some of them are also more good looking by some standard, and others are not as good looking by some standard. And perhaps it is the case that these two factors, so ability and how good looking you are, influence whether you become famous. So one could imagine that if you are extremely good looking, then perhaps you can become a model or an actor, especially also if you're also like really clever or have a very specific skill. Like Bill Gates, who's I guess not terribly good looking, but I guess had some valuable skills at some point. So if this story is correct, then by assumption, there's no relationship between IQ and looks. That's the story that the graph is telling. These are just two independent features of people. Some have higher ability, some have lower ability, some are better looking, some are not as good looking. There's just no relationship between those. And so here's a picture with simulated data where ability or IQ is on the x-axis and good looks measured somehow are on the y-axis. And if you just look at all the points, you can see that there's absolutely no relationship by assumption between those two variables. The regression line would be completely flat. There's absolutely nothing going on. Now, what does it mean here to control for the thing in the middle? Well, we could say perhaps you become really famous or a celebrity if you are both like pretty intelligent and able. So if you're on the right side here, and also if you are perhaps really good looking. So the blue line is like demarcates the line between celebrities and non-celebrities. So all the red points are those few people that actually become famous, either due to good looks or to some very specific, highly sought after ability. And so controlling for fame, one strategy for that would be to subset the data. So to just perhaps to throw out the black points, for example, just to keep in the red points. And if you imagine that you only kept the red points, so the celebrities in the data, then the data would be conditional on having high fame, conditional on being a celebrity, controlling for being a celebrity. And then you see, if you imagine fitting a regression line just among the red points, that there's a pretty significant negative relationship. And so why is that the case? Because if you are a celebrity and you have a super high ability IQ, then that alone makes it just more likely, that alone explains why you became a celebrity in the first place. And that means that you didn't need to be that good looking because your ability alone made you a celebrity. And reversely, if you are very, very good looking, that alone perhaps made you a celebrity in the first place. And that means that you didn't need to be very clever because your good looks alone made you famous. And so that explains why we see a pretty strong relationship, negative relationship between these two variables among celebrities, even though in the overall population, so if you look at the overall picture, there's absolutely no relationship between ability and looks. So to sum up, again, this is the collider path. Fame here is a collider. The path is blocked. If you just look at the overall data, there's no relationship between the x and the y-axis, the x and the y variable. But once you somehow condition or control for the thing in the middle, once you look at the subset of the data, for example, only celebrities, you get a relationship between IQ and looks. So perhaps there are questions on that. I see there's a discussion in the chat on that example by Stefan, but again, I think it would lead us slightly astray. But it does not seem there are questions on the IQ looks celebrity example. So just to be sure, because this sometimes is kind of counterintuitive, let me give you a second example of this collider structure, which is an example that I think is pretty plausible actually about research and research studies. So perhaps you know Science, one of the most prestigious scientific journals in the world. And it is probably the case that a research study gets published in Science if it's just a really well-made study that is really rigorous and well executed. But it is also the case, and at least either Science or Nature are also explicit about this in their policies, that if a result is kind of surprising or newsworthy, it is also just more likely to be published in Science. So if something is unexpected, and especially if you can imagine that something would make a good headline in a tabloid, then it just turns out that it's also more likely to be published in Science. And now this graph tells a story where some studies may be newsworthy, some others are not. Some studies are rigorous, well executed, some others are not. And I'm just saying with this graph, these two features are just completely independent, which perhaps is slightly unrealistic, but let's just make that assumption. And both of these features impact on whether that study eventually gets published in Science. So if I have data on how surprising or newsworthy a study is and how rigorous it is, I will see no relationship. But now, perhaps you read the newspapers and then you find that there's a report about a study that is published in Science. And so it's in the news. So apparently it's newsworthy. That's something you know, and you also know it was published in Science. So what does that tell you about how good, how rigorous, how well executed the study is? And the unfortunate fact is, if the study is newsworthy, if you read about it in the news, and you also read about it that it's being published in Science, it's probably less rigorous than average. Because the fact that it's newsworthy alone explains that it was published. And so it didn't have to be rigorous, at least not on average, to get published in Science. And so your rational expectation would be that it is slightly less rigorous, or even more, or substantially less rigorous than on average. And this again is a collider phenomenon. Okay, so if there aren't any questions on the collider thing, I'll just wrap it up real quick. We talked about, or I talked about, 3 graphs, 3 prototypical situations. The first one was, you can call a chain of mediation, where we said that the path is open, creates correlation, but once you control for the thing in the middle, it is blocked. The same thing is true for the second graph, which you could call common cause or fork or confounder. That path is also open, creates a correlation between the 2 variables, but that correlation vanishes once you control for the thing in the middle. And then lastly, I gave you 2 examples of collider phenomena where the path is naturally blocked, but becomes open once you control for a thing in the middle. So once you know whether a person is a celebrity, or once you know whether a study is published in Science, this creates correlation between those 2 other input variables that are independent in the general population. And so you can build any directed acyclic graph just by sticking together these 3 essential types of connections or paths. And then if you have a much more complicated path and you wonder, okay, are D and Y correlated? What happens to the correlation when I control for this or that variable? Then it turns out there's a criterion for you to determine that is called D-separation that answers that. And the definition is on this slide. And the definition is kind of complicated, but it boils down to, you look at D, you look at Y, or here I formulated as X and Y, and then you just write down all the connections, all the paths between the 2 variables that you are interested in. And then for each path, you check whether it is open or blocked, depending on which variables you would want or which you can control for. And so I think that's easiest, or that's more understandable by walking through an example. So we say that if we can somehow block every path by using some variables, we say that the 2 variables we are interested in are D-separated, controlling for the other variables. We also say that is a testable implication of the graph, because if we measure all the variables that are involved, we should see that there is no correlation if we control for certain other things. D-separation just means directional separation, because we're talking about directed graphs. Any path may be really long, doesn't matter, as long as you block a subpath, you block the whole path. If you look at the data and the graph says there shouldn't be a correlation controlling for this and that, but there is one, then something about the graph is wrong. That's why it's called testable implication. Okay, and I think we should do an example. That's going to be like a pen and paper example. We can just take 5 minutes to do it. Just a quick aside, there's also automated solutions. Perhaps the nicest one is DagGiddy, which has a website where you can just easily create graphs, and then the program automatically tells you whether certain things are D-separated. And there's also an R package for that. I'll not get into that because I honestly think that you should do that like 20 times by hand in order to fully understand it. But you are welcome to check out these 2 things, especially the website is very intuitive to use. And so here's an exercise for you. And this exercise will also lead us to later topics today. This is a graph where, again, there's an independent variable D, there's a dependent variable Y, and there's 2 mediators between D and Y. So there's like this path here, and this thing which you could call direct effect. And the question I have for you is, this graph makes many strong assumptions that I cannot even enumerate right now. Are these assumptions somehow testable? That is there a regression you could run using some or all of these variables to show that this graph is wrong? That is, are there any pairs of variables that should be uncorrelated, perhaps if you control for additional variables? And so I would just invite you to take a sheet of paper and take 5 minutes and think this through. I think it's reasonably complicated, but I would still invite you just to try to think it through. Think about all those variables and all those pairs of variables. Is there any pair of variables that should be uncorrelated? Perhaps if you control for other variables. Think about the paths that connect variables. Think about whether these paths are open or can be blocked. And you want them to be blocked because you want to find zero correlations. Take 5 minutes. Now it's 1:15. And then we take a poll. I guess we'll just take a tiny break. Okay, so if anyone desperately needs more time, quickly write it into the chat. If not, I'll proceed. And that does not seem to be the case. So I think we can just take a vote. Here's the link to the poll and see if anyone has any idea. Again, I think it's at this stage, if you haven't done it before, it's really tricky. So I guess you can just take a guess too. And let's see how far you got. Okay, so there's 4 people that chose the correct answer, so that's pretty good. 7 people chose the correct answer. Okay, very interesting results. Yes, I think I'll try to share the results with you because they're kind of interesting and really nice. So here you should see them. Let me. A pretty large relative majority says that M should be independent from or uncorrelated with N. So the 2 mediators, if you remember the graph, should be independent given the treatment or independent variable. And another 10% think that, no, sorry, another 10% think that N is independent from M. Oh no, I'm sorry again. So 44% think that the 2 mediators should be independent from each other given the treatment. And this is in fact the correct answer. So that's reassuring. And I guess that we have some people who've already done like this stuff or have a good intuition or just learned deseparation really quickly. And then there's quite a few who think that the independent variable should be independent from the outcome given the 2 mediators. So I'll quickly talk about that in a second. Yes, but the good news is that this is the correct answer and quite a few of you picked that answer. The other answer that many people gave that I think is also kind of intuitive is quite a few of you said that D and Y should be independent given those 2 things in the middle. And that is almost true because controlling for M and N in this graph blocks these paths, these, you could call them indirect effects that go through M or N. However, there's also a direct effect from D to Y that is not blocked. And so you would still expect to see a correlation between D and Y, even if you controlled for the 2 things in the middle, because there is a direct connection between D and Y that you simply cannot block somehow. Okay, so one strategy to solve this is indeed to just look at every pair of variables and check whether they are directly connected, because if they are directly connected, like D is directly connected to Y, D is directly connected to N, D is directly connected to M, M is directly connected to Y, N is directly connected to Y. All of these pairs of variables will probably correlate because there's a direct connection. There is no way for you to block a direct connection, so there's no way that these variables are ever de-separated. And so if you realize this, then in fact, the only pair of variables that could ever be uncorrelated is M and N, because there is no direct connection between those. So these two things seem like a good candidate to look into. And then if you zoom in on those two mediators, M and N, then you will see that they are connected either through D or to Y. So there's quite a few paths between them that I will not all enumerate, but for example, there's MDN, that is one path. There is MYN, that's another path, but there's also MYDN, that is also just another path, etc., etc. But if you look carefully at all of these paths, you will realize that either it's always like MYN, and then if you look at MYN, you have a collider structure. So this path MYN does not create a correlation between M and N because it is blocked, because it is a collider. And on the other hand, there's a few paths that go like MDN, which is a fork or a common cause. D is a common cause of the two mediators. So this would be a path that is open, that creates a correlation between M and N. But if you measure D, you can control for it, and then you can block this path by conditioning on D. And so it turns out that controlling for D blocks all the paths that exist in this graph. It also does not open up any others because it's not a collider on any path. And so we conclude M and N should be independent given D. And that's a really nice first result that quite a few picked correctly, either through walking through it or by having an intuition. And if you have measures of M, N, and D, one way to test this is to run a linear regression or any other kind of regression of, for example, M as an outcome on the other mediator controlling for D. And then the coefficient on N should be 0 if this graph is correct. And if it is not 0, then something about the graph is wrong, and there must be some other open path that you have not included. Okay, so if there are any questions, I see that Joris has pointed out that there's a typo on the slide, and I think you are correct. Yeah, so I wrote here the only open path is MDN, and the first arrow has to be reversed. So that's just a typo. So thanks for the hint. It's a confounding path. Are there any other questions on this example or on D separation more generally, or on causal graphs? Okay, so the good news is that, and Johannes asks, what do we learn by this for our regression then? So this is going to be the next step, because if you understand D-separation, then you can pretty much solve every problem that you could pose to a causal graph. Because when you understand D-separation and open paths and blocked paths, then given a causal graph, you can determine exactly what kinds of correlations you should see or not see, depending on what you control for. And so now we are in a situation where it's going to be extremely easy for us to find a good rule about choosing control variables for causal inference. So just in 1 minute. And then there's a YouTube question. Is there also a typo in the second arrow? So is there any other typo? Yes. So I'm sorry. So this sentence with the only open path that's just completely wrong. That's just a horrible typo. So sorry about that. If you look at the graph, D influences M and N. And so that should be a fork, and that should be here in the fifth point. Sorry about that. That's just it's a really messy typo. Any other questions on this? All right, and then I think we can accelerate the pace just a tiny bit, because now we have a really good foundation for all of the other topics, and we can actually get back to causal inference and causal effects and control variables. So let's talk about the so-called backdoor criterion, which is this rule for choosing control variables. So just to summarize, we now know which graphs create correlations or non-correlations depending on which variables you control for in your analysis. And we can use this knowledge to determine valid control variables really easily. And for that, we return to this really simple graph, which we could apply to that study that I talked about, where D was whether an individual experienced violence, Y was that individual's attitudes towards peace and violence, and where the author in that study argued that there were at least two variables, X, that influenced both the experience of violence and what you think about peace and violence. And the interest in that study is in the causal effect of experiences of violence on attitudes towards peace. And so the interest in that study, if we take this simple graph as given, is just in this arrow that goes from D to Y, because that hopefully intuitively signifies the causal effect of D on Y. And then the question, of course, is how can we determine this causal effect if we measure X and D and Y? And that is hopefully intuitive that if we were to look just at the association between D and Y, then we know now that this association mixes up two things. It mixes up the causal effect of D on Y. So this directed connection, the causal effect right here. And the second thing that it mixes up is what we could call the confounding due to X. So the open path dxy. And so clearly, if we wanted to isolate just the causal effect, because if we're interested just in that thing, then technically speaking, we are saying we want to estimate, for example, the average of Y given an intervention on D, given if we could somehow intervene on whether individuals experienced violence or not. And the mathematical notation is either using the do thing here, the do operator, or the potential outcomes notation, which is not important right now, but that's just saying we want a causal effect of D on Y. And so if we cannot expose people to violence at will in the experiment, in general, we need to find control variables such that bad or spurious or non-causal paths between our independent variable and our outcome are blocked in graph terms, and all the causal paths that we are actually interested in are left open. And so in this easy case here, the good causal path that we are interested in is from D to Y, and the so-called non-causal path is D to X to Y. And so I hope it's intuitive that we should control for X in this case in order to determine the causal effect. And just to be clear, this exercise of finding the appropriate control variables is logically unrelated to deseparation. So deseparation is just a thing that occurs depending on what your graph looks like. Sometimes certain variables are deseparated and sometimes they are not. If they are, by definition, then all the paths can somehow be blocked, and that is just a fact about the graph that one could use or not. For identifying causal effects, we certainly would always want to leave certain paths open, namely those causal effects, those paths that correspond to causal effects that we are actually interested in, although we also want to block some paths depending on the question we are asking. Okay, and so the rule that flows from that is called the backdoor criterion. And here's the precise definition. So given an ordered pair of variables d and y and DAG, a set of variables, a set of control variables x satisfies the so-called backdoor criterion if no control variable is a descendant of D, that is to say, no control variable is causally influenced by D. And secondly, the control variables X block every path between the independent variable and the outcome variable that contains an arrow into D. That's very compact, so let me explain what is going on here. First of all, we are saying it's an ordered pair dy because we're saying D is the cause, y is the effect. D is the independent variable, y is the dependent variable. So it's asymmetric. The question we are asking is asymmetric. It's a cause-effect question. No node is influenced by D. No control variable is influenced by D. We'll see in a second why that is very important. And the second requirement is block all the paths that start with an arrow into D and go to the outcome. And these paths are called backdoor paths because they enter the independent variable through the back door from behind. And so blocking all the backdoor paths makes sure we block all the bad paths because these are the paths that create correlations between independent variable and dependent variable, even though there may not be a causation of the independent variable actually influencing the outcome. So that's this backdoor logic. And the requirement not to control for anything that is influenced by the independent variable. So not to control for anything that is a descendant of the independent variable has two functions that we'll go into in just a second. It makes sure we leave all the good causal paths open that we are interested in. And it makes sure that we do not open up new paths that we do not want to have open. So that's quite a bit, I guess. There's also a few questions in the chat. The YouTube question, I don't fully understand, unfortunately. And Racha asks, isn't D independent while Y is dependent? Yes, that's the case. Maybe I mixed it up when I said it. But yes, D is the independent variable and Y is the dependent variable, the outcome. So maybe I mixed it up at some point, but I think it's clear. And then Tim has yet another question. Okay, so Tim has a good question. Yeah, thanks, Olga. Yeah, I think I think I have to skip that. But Tim has a good question about deseparation directly still. Okay, I'll try to remember Tim's question and maybe talk about it after the lunch break, like after we've rested for some time, because I think I want to go on with Backdoor criterion before the break, and then I'll try to address some of these questions later. I think that's what I'm gonna do. So the Backdoor criterion is really useful, I think, because it's reasonably easy to understand, and it's a rule that tells you what to control for, and it's actually correct. So remember that I gave you like 7 options, 7 different rules that many people use in practice, and 6 of these rules were just wrong, and they would lead you to controlling for stuff in some situations where you shouldn't. The Backdoor criterion is a pretty understandable rule that is 100% correct, that is provably mathematically correct, that determines what you need to control for, if you can. And it works for any directed acyclic graph. So no matter how complicated it is, as long as you're interested in one independent variable, one dependent variable, you just can do the work by hand and determine it, or you can use DAGGIDI, the one website or program that I referred to earlier, which also automatically tells you, given a graph, what you need to control for if you are interested in a certain causal effect. And now the interesting bit in the rule, I think, is this thing about the descendant of the independent variable. And so let me walk through this just before the break, because that's related to a phenomenon that is called post-treatment bias. And there's 2 graphs that we need to understand what is the problem here. The first graph we've seen before, it's just this chain of mediation. D influences M, M influences Y. No other variable, nothing else going on. It's unrealistic, but let's just assume that it's true. And now you could ask, okay, if I measure D and M and Y, and I'm interested in the causal effect of D and Y, what do I need to control for? And the answer, and I hope that's intuitive, maybe not, maybe it is you shouldn't control for anything. You should just do a regression of Y on D, because there are no backdoor paths. There is no variable that enters into D. It's basically, the graph would also apply actually to an experiment, perhaps, where you randomize D, and there's no other variable that can influence it. And so a simple regression or a simple comparison of means, if D is binary, would give you the average causal effect. However, it is also true that M clearly may correlate with both the independent variable and the outcome, because D influences M, so they're probably correlated, and M probably influences Y, so they're also probably correlated. And so you may say, and that was also the one rule that many of you picked, if there's a variable that correlates with the independent variable and the dependent variable, you have learned in statistics that you should control for it, because otherwise you have omitted variable bias. Unfortunately, that is not true. And indeed, in this graph, we know from D separation, there is just one path between D and Y. It goes through M. Once you control for M, you will see no relationship anymore between D and Y, because you controlled away the causal effect. And so the regression will tell you that D does not affect Y once you control for M. And that's not true, because D does in fact affect Y. And if you make the mistake of controlling for a mediator, then the regression will simply give you a wrong answer. And that is the first reason why you should think very hard about what you should control for or not control for. And in this case, if you're just asking, okay, what is the effect of D on Y, you must not control for M, because you would block away the causal effect that you are actually interested in. That's a pretty important point. So are there any questions? Yeah, so Christian asks about the direct effect of D on Y, which is a separate question where a separate rule applies. I'll talk about that after the break. Yeah, but here, and this is super important to be clear about, we're just saying we're only interested in D and Y. Anything else is just a potential control variable. We want to know the overall causal effect. And in this graph, you are totally fine with just running that one regression where you do not control for anything else, just Y on D. And in fact, you're kind of better off if you hadn't even thought about M, because M, for your question, what's the overall causal effect? M only creates problems. For other stuff, we'll talk about that later. Any other question? Okay, nice. Then I just have like one more graph about, and then we can conclude post-treatment bias, and then we can go into the break around 12, I think. Yeah, so perhaps as an aside, or not an aside, pretty important point, this practice of controlling for variables that are influenced by your independent variable of interest, even though you're just interested in the overall causal effect, that is very, very common. And there's one paper from political science that estimates that, for example, about 50% of all experimental studies do that, even though they really shouldn't do it. So it is a very big problem in applied research. And so that's also why I focus on it quite extensively. Nguyen has a question. What if I run a linear regression, including M, and the independent variable still has an effect? Then what would the causal diagram look like? That's a good question. So in this graph, if we think that this graph here is correct, and we forget the causal inference question for a minute, then it's just a fact that M, the variable in the middle, the mediator, D separates D and Y. And as I said, that's just a fact, and that is something that you can check by running a regression of Y on D and M. And if you then find that even if you control for M, there's a relationship between Y and D, then something about this graph has to be wrong. There has to be an open path between D and Y, and there could be multiple answers to that. So there could be a direct effect from D to Y. There could be a confounder influencing D and Y, or both, or other more complicated things. It's a good question, but it's a separate question because it's about D-separation and about testing the graph. And for that, you would want to control for M, because then you shouldn't see a correlation according to the graph. If you are focusing on the causal effect of D on Y, then you must not control for M, because you will get the wrong answer. And Ofer has a slightly more technical question. What happens if there's a descendant of M? So perhaps I could just quickly annotate it. I think you are thinking like this. So M star would be a descendant of M. If you control for this, then something similar will happen. It will not completely block the connection between D and Y, because M star would be like an imperfect proxy, but it will still change the relationship between D and Y. And it will give you the wrong answer in terms of the causal effect. And that's also why it's forbidden by the backdoor criterion. Good question. Okay, so if there aren't any more questions, then I'll quickly show you a second problem with these post-treatment variables. So I hope that this problem here, where you control away part of the effect that you are actually interested in, is reasonably intuitive. But there's also a second, more intricate problem that you can really only understand if you know how causal graphs work. And the graph for that second problem is this one here. So this is slightly different. D influences M, but D does not causally affect Y. That is very important to realize. There is no directed arrow going from D to Y. It only goes through M, but then stops. So if we assume that this graph is true, then we are saying definitely that the independent variable D does not causally affect the outcome because we have deleted all causal effects from D to Y. And that is just an assumption that this graph communicates. However, there's another variable U that perhaps is unobserved. That's also why I called it U, and I also dashed it to indicate that it's potentially unobserved, so potentially not measured in your data set. And then you can ask the same question. So you can ask, if you are interested in the causal effect of D on Y, is there anything that you must control for? Is there anything you must not control for? And the answer by the backdoor criterion, again, is very simple. There is no backdoor path into D, and so there's nothing that you must control for. And secondly, M is a descendant, is causally influenced by D, so you must not control for M. And then you would run a regression simply of the outcome and the independent variable, and the regression will give you the correct answer, and the correct answer is that D does not affect Y if this graph is correct. Now, what happens if you do control for M? Then again, that may seem like a good idea because M correlates with both the independent variable and the outcome variable. And again, that's something that many of you said is like a precondition or an indicator that you should control for this in your regression. Why is that the case? Because D influences M, so they are probably correlated. And then M and Y are also connected through an open path, a backdoor path, if you will, from M to U to Y. So that's basic confounding that will also, in all likelihood, create a correlation between M and Y. So again, applying this bad rule of choosing control variables, you could say, I've learned in statistics that I need to control for M, otherwise I have omitted variable bias. But what happens, it's a really bad idea, because there is one path between D and Y that goes D, M, U, Y. That's a path that involves 4 variables. And M here is a collider between D and U. So that path is not causal, but it is blocked because M is a collider. There is no relationship between D and U, and therefore there's also no relationship between D and Y through that path. However, once you control for M, you control for a collider. I gave you two examples. When you control for a collider, the thing in the middle, you create a dependency between D and U, and by extension, you also create a dependency between D and Y. And so if you run this regression of Y on D controlling for M, you would see that the regression coefficient for D is in fact different from 0, which is the wrong answer, because if you are interested in the causal effect, then that causal effect is definitely 0 in this graph. And that may be perhaps not terribly intuitive if you're not used to causal graphs. So if it helps, I've in the Colab, there is also some simulation code that illustrate this phenomenon. So let me quickly switch to Colab and show it to you. Here we go. There we are. So this is my Colab. I hope that by now you've run the first snippet installing the packages, because we'll use that after the break. Here's a bunch of code for the stuff I've talked about prior. And this part here is a quick simulation for post-treatment bias. Perhaps as an aside, the set seed function just makes sure that the example is reproducible. And then here, I created some treatment variable that has 1,000 observations from a standard normal distribution. U similar has 1,000 observations from a standard normal. D and U have absolutely no built-in relationship. And then M is influenced by D and influenced by U, and also has some noise. And Y is only influenced by U plus some noise. And here, this is just a simulation that directly translates the graph that I just showed you into equations in R and simulates data from it. And it should also be clear that just if you look at the equation for Y, D does not affect Y, because there's no D that pops up here. There's also no M that pops up here. So neither D nor M causally affect Y by design. And then if you run this, it takes surprisingly long, you can run the first regression of Y and D. This is the first result here. The coefficient on D is basically 0, which is correct because D does not affect Y. However, once you control for M, you actually get a large negative relationship between D and Y due to this collider structure. So that is just a simulation to confirm the argument I made using open and blocked paths. There's a question in the chat about 2 pluses. Oh, the 2 pluses are a typo. Okay, that's funny. Why did it work? Huh, that was just a funny typo that didn't make a difference. You never stop learning. Okay, so before we go into the break, let me just quickly wrap up. Post-treatment variables can seriously create problems in your study if you are interested in causal effects. And a graph that combines these two phenomena is this phenomena. And this graph, D has a causal effect on Y through M and directly. And you also have this unobserved confounder that influences M on Y. And now in this graph, again, there is no backdoor path into D. Perhaps you randomize D, or you block backdoor paths using other variables that are not shown in the graph. But basically, you don't have a problem. a simple regression of the outcome on the independent variable will do the job, will tell you the average causal effect. However, once you control for M, you introduce two problems. You block a causal path, so you block D to M to Y, which is not good because that's part of the overall causal effect that you are interested in. And secondly, you open up a new non-causal path, which goes D to M to U to Y because of the collider phenomenon, which you also do not want. And these two phenomena can occur both at the same time. They introduce bias if you are interested in the overall causal effect. And this bias basically can go in any direction. So it could lead you to overestimate the effect, to underestimate it. Just that depends on the specifics of the data. Okay, so final remarks on this post-treatment stuff. I think that is still not terribly well known. And so that's why I spent some time explaining it. In fact, it's usually not mentioned in textbooks, at least not in textbooks that are older than 5 years, say. And even if it is mentioned, it is often also not really well explained. So a bad explanation, I think, for that phenomena is, for example, in Mostly Harmless Econometrics, if you know the textbook. And so that is something to keep in mind. All right, so that concludes everything I wanted to say about the backdoor criterion. And now is the perfect time to take a break. And after the break, we'll talk about sensitivity analysis in R. And then we'll switch to causal mediation and perhaps also to instrumental variables. If you have any more questions, you can write them into the chat. And then we'll see each other again around 20 past 12.
What did you say?
Huh? What?
Go on.
Okay, I'm back. I hope everyone else is also back. There were quite a few questions before the break and also in the break, and I would take 5 minutes to try to answer them because they were all really good. And then right after, we will use Colab a bit more. So if you haven't done it yet, go to Colab using the link and make sure you have run the install packages thing, because that will take about 5 minutes. And alternatively, if you are using your own R Studio, whatever installation on your PC, also make sure you have access to Colab, and so that you can copy some of the code, perhaps that should make it easier. But let's start with some questions. So everyone should see my screen now, the slides. So some of these go kind of deep, so you may also choose not to listen. I don't know. Stefan had a pretty intricate question about, I think, this simple chain of mediation graph, where he said, okay, what if I flip a coin, D, which decides whether I use another coin, M, which I guess then you would also flip to decide whether you go to the cinema. I can, two things, so that's not how I decide to go to the cinema, but perhaps other people do it. And it's an interesting question from a graph perspective, because there will be no observed correlation between D and Y when you think it through, because D is like a coin flip, so it's like random, and then it randomly determines just what kind of coin you use in the second step. But then that result of that second step is random again. It's literally just a coin flip. And so Y kind of only depends on M and not empirically on D. And so if you do this, if you simulate this, for example, you will not see a correlation between D and Y. Is that a problem? And it's some problem. In technical terms, that's a violation of what is called faithfulness. The graph would suggest that you should see a dependency between D and Y, but just the way you set it up, it's like fine-tuned in a sense, so that you do not actually see a dependency between D and Y. And for testing this graph, and for D-separation, it's not really a problem, because you will just find that Y and D are uncorrelated no matter whether you control for M or not. Given this story in this graph, this is also correct, and there's nothing you can learn, but it's like the correct conclusion. On the other hand, this stuff like this is more of a problem if you do like the reverse task. Given some data, let us learn the graph by looking what correlates with what and which correlation vanish if you control for additional stuff. And here, of course, you would find that D and Y are uncorrelated, so you may wrongly infer that there's no connection between them in the causal graph, which is wrong. But that's an entirely different problem. So that is causal learning. That is a very different problem that I'm not going to talk about. And it's more of a problem for that exercise. So I hope that somehow answers the question. Then there were a few other really nice questions on YouTube and also here in the chat. And one, if I understood it correctly, basically asked, what if there is mutual causation? So D influences Y and Y influences D, or D influences U, and U influences D. And then no matter what the exact things are, nothing of what I said applies, or at least does not apply directly. So everything I said was assuming that we have a DAG, and remember that the A in DAG stands for acyclic. So you must rule out cycles a priori. If you cannot do that, then you cannot apply any of the things that I talk about, and then you will have much more complicated problems, and there are no easy solutions for any of these. So stuff just becomes much more complicated, and that is also much of that is also like an open research problem. So that's like cutting edge research and statistics and machine learning. Then there was a great question that often comes because people are irritated because they think about interaction effects, and then it's not really clear how you would display an interaction effect in a causal graph. And the short answer to that is you don't. And the longer answer was really beautiful phrase by Will in the chat. So I'll just copy his answer. Interactions in the statistical sense or in the causal sense are not represented. It's deliberately left out. It also wouldn't really make a difference. I'm sorry for the typo that I messed that up. If you say that A and B influence Y, you are implicitly saying that A and B can interact in very complicated ways in determining Y. And all of what I said, the backdoor criterion and D-separation, although I, for practical reasons, focused on linear regressions, all of what I said goes through in arbitrary, complicated data with complicated models, with complicated interactions. It doesn't matter. This causal graph stuff is very general and also applies to more complicated functional forms. Okay, so that was about interactions. And then Edward asked, is it right that what you, so that's me, have taught so far might not be well reflected if we stick to the so-called potential outcome framework? That's a nice question. Well, the short answer is yes, that is right. I don't have time to elaborate on that, but I guess if you've read some textbooks using this, that only use the so-called potential outcomes framework, some of the issues that I talk about are really hard to understand using that framework, like, for example, post-treatment bias or this collider phenomenon. You can do it in potential outcomes. You can translate everything that I have said mathematically into something that only involves potential outcomes and other variables, but it will usually become much more complicated and not as intuitive as the things that I have talked about, especially when it comes about like what is correlated with what condition on other variables. So this whole D-separation thing, backdoor criterion, choosing control variables, post-treatment bias is definitely easiest to understand from a causal graph perspective. And then one final thing, and I'm sorry that it's cut off, Johannes asked, could you elaborate on how you use DAGs and regressions for testing, maybe correcting the DAGs and finally choosing control variables and regression models in real world science? I figure it's kind of an iterative process, and that is absolutely correct. So the short answer is yes, you would try to come up with a graph in the first place. Yeah, I'll add a point to that later. Then perhaps you can test it using D-separation. Usually you cannot, it's very rare. Usually if you think that you can test it, if there is some kind of D-separation going on, then in almost all cases that I know, or in many cases, most cases, the graph is just hopelessly unrealistic and you should reconsider it. But sometimes it happens and then you can test it and then maybe it holds. Maybe it doesn't. If it holds, you can use the backdoor criterion to answer further questions about what you need to control for. If it doesn't work, if some test fails, then you need to reconsider the graph, and then perhaps check the backdoor criterion again, and then check whether you can answer a certain question or not. So yes, it may well be an iterative process. All right, these were questions from the chat. There were one or two that I'm going to address anyways in the course. If there isn't anything else, I would go on in the program. And maybe a good bridge to the next topic is actually Johannes's last question. Because in real world problems in social science, but also in other disciplines that use data, in almost all cases, you have unobserved confounding. And then that's something you need to deal with. And one really nice constructive way to deal with it is called sensitivity analysis. And that is the thing that I want to talk about next. So here I'm still sticking to that study by Hazlett about violence in Sudan and whether people experience violence and whether that affected what they think about peace in their country. So again, D stands for individual, or measures individual experiences of violences in the past. Y is what people state in a survey, what they think about, whether you should make peace with former enemies and some other stuff. And then I've already mentioned that Hazlett argues that there are a few other observed variables, X, including the gender of a person and the village where that person lives, that determines both D and Y. And if it were only for that, we would have a very simple graph where there is one backdoor path from D to Y going over X. We can control for X if we measure it, and then we can adjust for it in a statistical model, and then try to estimate the causal effect of D on Y using some kind of regression approach. And I've already showed you some results that indicated that if you control for some things, then it seems that D has a relatively large positive effect on your supportive peace. So that means that it seems that experiencing violence positively affects or makes you demand peace, so that violence does not beget violence. But, and this is something that Hazlett himself nicely discusses in the paper, it may well be that we have a few more unobserved confounders. So here I've called them U, that also influence D and Y, and that create an additional backdoor path, or actually two additional backdoor paths that we cannot block if we do not measure U. And so then what are we supposed to do then? The backdoor criterion would tell us that we must control for U, but if we cannot measure it, we cannot control for it, and then we cannot estimate the causal effect we are interested in. And so either we just stop the project at this stage, or alternatively, what we can do is we can think about how strong possibly the influence could be, or the relationship could be between those unobserved confounders and D, the independent variable of interest, and the unobserved confounders, and Y, the dependent variable of interest. And it turns out that if you stick to a linear regression framework, then one can very easily make some assumptions or try to gauge how strong these relationships would need to be in order to substantively change your estimate. And what you do is, it turns out that there's only two things you really need to think about. The first one is the relationship between U and D, and specifically, there was some sound that I didn't get. Okay, I guess that was just a mistake. The relationship between U and D, and specifically you need to think about, there are these variables U that you didn't measure. how much variance would they explain in the treatment beyond that what the observed variables x do. So this funny symbol here is an r squared relating to, or saying, this symbol basically says how much variance does u explain in d when you have factored in x. So technically that is a partial r squared, and that is going to be a number like u explains an additional 5% of the variance in d, or u explains an additional 20% in the variance of d. So it's going to be some number between 0 and 1, or 0 and 100, and you interpret it just like the r squared that you all know from basic statistics. It's like variance explained. So that's the first thing that you need to think about. And the second thing is very similar. It's the r squared, or the variance that the unobserved confounders simultaneously explain in the outcome, having factored in d and x, so the independent variable and the observed controls. And here again, this is a number that you need to name, a number between 0 and 1 that says all of these unobserved confounders explain 1% or 5%, 10 or 20 or 50% of the outcome, having accounted for d and x. And that is the basic setup, and that's how it relates to, or how it possibly relates to a causal graph. And what I would like to do, well, and this approach is implemented in a very nice R package that is called SenseMaker, that by now hopefully everyone has installed either in Colab or in their local R session. And I'll show you some basic output from that package, and it looks like this. And this may not be terribly intuitive, so we need to slowly talk about what this graph tells us. So this is a so-called contour plot because it actually has 3 dimensions. It has an x-axis, which is a partial r squared of the confounders, so of the u with the treatment. So that corresponds to the partial r squared that describes the relationship between u and the independent variable, the d, in the previous graph. And on the y-axis, and here this r squared possibly ranges from 0 to 0.4. That's just how the plot works. And on the y-axis, we have the other r squared that describes the strength of the association between the unobserved confounders that unfortunately we cannot measure and the outcome, so the dependent variable, the y. And we start in the bottom left with the black triangle, and that is the situation where we assume that these unobserved confounders actually have no relevant relationship with either the treatment or the outcome. So here in the bottom left, we're saying the relationship, the linear relationship between the unobserved confounders, even if they exist with the treatment and the outcome, is just 0. And that is, of course, the default assumption that you just get if you just run the standard linear regression just using the observed variables. And in this particular data set, it turns out that if you do not control for anything, if you just run the regression of attitudes on violence, the point estimate that is demarked here is 0.06. So that means that individual experiences of violence increase support for peace by 6.3 percentage points. And that is unadjusted in the sense that it does not at all adjust for these possibly unobserved, possibly existing unobserved confounders. Okay, so I hope that is clear. And then what the plot then tells us is how this original estimate of 6.3 percentage points would change depending on how strongly associated these hypothetical unobserved confounders are with the treatment and the outcome. And for example, this line here, this first line, depicts combinations of strengths, so combinations of the unobserved confounders having a particular correlation with D and a particular correlation with the outcome, such that the estimate, if you could somehow adjust for the unobserved confounder, would be 0.05. So you can see this small number here. And so that line tells you, for example, that if the unobserved confounders explain 30% of the variance, of the additional variance in the treatment, and like if you go to the left, very, very, very little at the same time, so like close to 0% in the outcome. And if you could, and then if you were to adjust for these unobserved confounders, then your point estimate would change to 0.05, which is just a small change. On the other hand, the red line indicates combinations of R squared for which your point estimate of 0.063 would actually be 0 if you could somehow adjust for these unobserved confounders. So for example, if the partial R squared of the confounders with the treatment is like 0.1, and at the same time is like, I guess, 0.8 or something with the outcome, which doesn't seem very strong. So then we're just saying, okay, these hypothetical unobserved confounders explain 10% of the variance in the treatment and close to 10% of the variance in the outcome. Then that alone would be sufficient to, if you could then adjust for these, then the point estimate would move to 0, which of course would totally change the conclusions of the study. And then beyond the red line, these are lines where the point estimate would actually switch signs. So this is minus 0.05, minus 0.1, minus 0.15, and so on and so forth. And that would happen if these unobserved confounders were even stronger. So for example, at this point here, the hypothetical unobserved confounders would need to explain 20% of the variance in the treatment and 10% of the variance in the outcome. And that alone, if you are unlucky, so to speak, could mean that the actual estimate would be minus 0.5 and not positive, which would totally change your conclusions. Okay, and this is basically how you read this plot, and you should have in mind that it's connected to some graph that looks like this, where these two R squared parameters parameterize the relationship between unmeasured confounders and the independent variable and the outcome. Are there any questions on this? Okay, Johannes asks, why can't the factor get higher than 0.63? That's a great question. So the question basically is, why isn't there anything to the left of the unadjusted estimate? Why can it not always also be more positive than 0.63? And the answer is it definitely can be more positive. If, for example, the unobserved confounders positively impact on independent variable, negatively impact, sorry, on independent variable and outcome. So forget about that, that was wrong. But it definitely can happen, but it's inconsequential because the whole idea for this exercise is, given that we have estimated a positive causal effect, we we implicitly know that it could be even larger, but we are more concerned about the opposite situation where it goes towards 0 or even switches sign, because that would change our qualitative conclusion from the study. And so that's why basically the plot is somehow simplified and only indicates situations where the qualitative conclusion would change in the sense that the estimate would become 0 or it would switch signs, because we are more concerned about that, at least in this case, than about the estimate being even bigger. Edward asks another good question. He asks, by unobserved variables, do you mean the variables that one cannot measure or one cannot think of, or both? I guess it's both. So when I introduced the example, the graph, that was not really nice for me because I didn't specifically name what any of these unobserved confounders could be. Because I'm not sure he does that in the paper, and maybe he does. But if you are serious about this, you should try to think about concrete examples about you that perhaps you would want to measure, but you can't. But on the other hand, this sensitivity analysis also works, of course, if you do not know what these variables actually stand for. What you only need to know, or what you need to put a number on, is these two partial r squared. That is all that matters in the end. But it's good scientific practice to be explicit about what the u could be or could not be. Any other question? Okay, so the challenge right now, I think, is how the hell would you come up with these partial r squared numbers? Because already in this plot, the plot tells it that it actually makes a huge difference. And already with kind of small seeming r squareds of around like 0.1, it could be that such an unobserved confounder would be strong enough to move your point estimate towards 0 or even make it negative. So it seems we desperately need to assess like how large these numbers can possibly be and whether it's realistic that they are below 0.1 or whether they're certainly above 0.2 or 0.3 or whatever. So that would be the next exercise, and that's an exercise that I have for you, which is called a benchmarking. But first, Ofer has a question and asks, would you say that a good result is when the red line is as far as possible from the 0, 0? That is exactly correct. So if the red line is very far away from this point down here, from the black triangle, then that means you need large r squareds in order to move the estimate hypothetically to the red line, which, all other things being equal, is less likely, because you would need to have strong unobserved confounders that simultaneously have a large impact on the independent variable and the outcome. And that is kind of less likely, informally speaking, if the red line is very far away from the 0, 0 point. Yeah, so that is exactly right. Okay, but then again, that also means that we somehow need to get a grasp on whether these numbers, what these numbers means, these partial r squareds. And now what I would ask you to do is to go into the Colab, and there's some basic code already there that uses the SenseMaker package to produce exactly this plot. And I would ask you to run an additional regression with the independent variable that is called something like experienced violence, I think. And you should add gender and village as control variables, and then use gender for so-called benchmarking. And in abstract terms, what the code should look like is that you create an object, some name, you use the function that is called SenseMaker. You give to that function an object that is your linear regression, which includes gender and village and the independent variable. You declare the name of the independent variable. So I'll look it up in a second. I think it's something like experienced violence or something. And then you also name the name of a so-called benchmark covariate, which here that name should be gender in inverted commas. That creates a sensitivity object that you can then plot, and then that's going to be an interesting plot. And so I'll try to switch to Colab to show you what is going on. Just give me 1 second. Here we go. Here we are. So we are in the section that is called sensitivity to unobserved confounding. You first need to load the library to activate the package. And then this code here creates the plot that I just had on the slides. So you run a basic regression. The independent variable is called directly harmed. The data set is called Darfur. Before you need to load it using this command. Then you create a sensitivity object. You name the model that you've run. You name the treatment. The other thing is not that important. And then you can plot this thing, and it's going to look like the plot that I just showed you on the slides. And now again, I want you to change the model here, include gender and village, and then declare a benchmark and covariate, and then plot it again. So I guess I'll just give you a few minutes to implement that. And I will actually get some water because I'm very thirsty. So see you in a minute. All right, and if I don't hear anything in the chat, then I'm just assuming it's going well with the code for everyone. There's a good question from Nguyen asks, oh, right. So Nguyen is right. Yes, so sorry about that. The gender variable is not actually called gender, but it's called female. That's my mistake. That was a typo. Yeah, sorry about that. So the variable is actually called female, and it's a dummy that indicates whether a person is female. Okay, I think I'll just slowly proceed. There's one more question from YouTube. Yeah, that I'll quickly answer. The question is why you would only need to be concerned about the R squared. The R squared doesn't have a sign. So for this package, you do not need to think about the direction of the influences of the unobserved confounder. And the question is, why don't you have to do that? And the answer is that this is basically going on in the background. And it's also the same answer that basically the same answer to the question from Johannes earlier, depending, so I'm going to share my screen again, just to make that clear. Depending on the direction of the influences, the point estimate would either become smaller or more negative, or become larger. But the package implicitly assumes that you don't care about situations where the sign stays the same of your estimate and becomes larger in an absolute sense, because that is always possible. But here we are more interested in this switching of signs. And so that computation, that relates to the sign of the unobserved confounding. And that is kind of in the background. And that's why you do not need to concern yourself with the direction. You only need to mention or name a certain R squared value. Yeah, so that's the short answer, basically, because we are only concerned about switching the signs of the estimate. Okay, so I'm assuming that perhaps people have managed to run this benchmarking exercise. What the code should look, or the plot should look like. First of all, oh, sorry, I don't have, I need to share the code with you. I forgot to insert that into the Colab. So I'll just insert it real quick and save it. And then you should be able to see the code in Colab. Maybe you need to refresh it. That's possible. But at the end of the day, what the plot should look like is this here. So it's very similar to the previous plot. A few things have changed. One thing that has changed is the value of the original point estimate. So it's now 0.097, so basically 10 percentage points, which is due to the fact that we added control variables. We added gender and village as fixed effects. And so that actually makes the estimate like 50% larger. So before it was like 6, and now it's like close to 10, which is good. And that also relates to one of the previous questions. You can already see that because the estimate is larger in an absolute sense, it's now 10%, the red line has actually moved away from the unadjusted estimate, which is adjusted for gender and village, but not adjusted for potential unobserved confounder. That's confounders. That's why it's called unadjusted. And that's a basic, very basic lesson. The bigger your point estimate, the more robust it is to unobserved confounding, simply because you need stronger unobserved confounders bringing a large point estimate down to 0, or having it switch signs. So a crude sensitivity analysis always says the estimate is so large that it has to be causal, even if there's some unobserved confounding. Okay, and that's why the red line kind of moved away from the original estimate. And the other thing that has changed is we have 3 additional red squares, kind of. And these squares use this female control variable for benchmarking. So the first red square here tells us that if these unobserved confounders, which we did not measure and which we perhaps do not even know what they are, if they are as strongly related to the independent variable as is female, this observed control variable, then And if you could then adjust for these confounders, then your point estimate would change to this location. It would change to 0.075, which is not a lot. And accordingly, these other points tell you that if these unobserved confounders were twice as strong or 3 times as strong as the observed control variable, in the sense of these r squared, then in the worst case that is depicted here, your point estimate would shrink towards 0.03, which is much smaller than the unadjusted estimate, but still positive and not entirely trivial, I would see. And so, in a nutshell, this is a really neat exercise that tells us that it seems that this estimate is not very sensitive to unobserved confounding, in the sense that the unobserved confounding would need to be much stronger than the observed confounding through gender in order to change the substantive results from the study. And in that concrete study, Hazlitt actually argues that the gender variable was pretty important because the militias targeted women with violence more than the men, if I remember it correctly, or at least he argues that this was actually kind of important. And so that plot is basically reassuring us that our simple estimate is relatively robust to unobserved confounding in this specific sense. Are there any questions on the sensitivity analysis? That does not seem to be the case. Then I can conclude this by just a few additional comments on what is going on behind this approach. So all of this relies on an important assumption in the sense that if you could measure the unobserved confounders, then you would also just run a linear regression. So all of this critically depends on sticking to a linear regression framework. This also allows you to use these relatively simple R squared measures and to do this cool comparison with the other control variables. And so if you think that a linear regression is not appropriate for your data, then you should not use this approach. But on the other hand, the paper that this is based on by Cinelli and Hazlitt shows that the unobserved confounders may actually be many, many different variables that impact on the independent variable and the outcome in very complicated ways. That all does not matter as long as you stick to this linear regression framework. And that is due to the beauty of linear regression, that even if the actual relationships are very complicated and non-linear, what matters for your estimate is just like the linear relationships. And so that drastically simplifies everything and also makes it kind of more realistic, because you do not need to concern yourself with the question about whether U is just one variable, whether it's binary, whether it's metric, or whether it's 15 variables, and so on and so forth. The only thing that matters in the end are these two R squared values. So it does not get any simpler than that. And then, of course, right, so there's two questions. Ofer asks, is there a sensitivity analysis that works with generalized linear models, so like Logic, Probit, Poisson? I'm not aware of general purpose solutions for Logic or other GLMs, unfortunately. I guess if you look long enough, you'll find maybe some packages. I don't know any by heart. This particular package is pretty new, so the article is from last year. So I guess it's also ongoing research to extend this to other kinds of regressions. But let me reiterate that there will be a trade-off, I think. On the one hand, here you need to stick to linear regressions, which may be not appropriate. On the other hand, in this approach here, you don't need to make any assumptions about what the U looks like. And I'm pretty certain that if you switch to something like a logit, you would need to be much more explicit about what the unobserved confounders, what their distribution is basically. And so you would need to trade off some assumptions. And so in summary, I think that this approach here with SenseMaker by Chinelli and Hazlett is pretty powerful, and it's probably a good idea to use it. Then there's a question from YouTube that asks, can you run this type of sensitivity analysis with a panel regression? And the answer is yes, as long as your panel regression uses a linear model, and specifically the linear model function in R. So that's the LM function. So in the worst case, if you're using fixed effects or something, maybe you've worked with PLM instead of LM, because that's faster and smoother. And then for this, you would just, for example, manually include fixed effects in order to do this. But as long as you can do this, as long as you stick to a linear regression framework, which in panel analysis is still dominant, I would say, then you can also use it for panel analyses. And also nothing substantively would change about the analysis, I think. Perhaps one thing to have in mind is that for this benchmarking exercise, you need to name, you cannot, for example, you cannot benchmark using all of the fixed effects because the fixed effects are like n different dummy variables. So that's not something you can do. You need to name specific variables. Okay, and then just perhaps two concluding comments. You can also assess the sensitivity of your significance tests using the package. The code is here on the slide. You just declare that you want to investigate the sensitivity of the t value, and then the red line is not at 0, but by default at 1.96, which means that is the 5% significance demarcation line. All right, and let me reiterate that I think this is a great package. It's great implementation. I think it's reasonably intuitive to understand. And if you work with observational data, you should use it. And I think it increases the quality of every single study that you would do. It's always a good idea because, especially in the social sciences, it's very realistic that you have some residual unobserved confounding. So if there aren't any more questions, then this would kind of conclude the main part of the workshop. And let me just quickly summarize what we've covered. I started with the simulated data with the additional control variable, where I showed that statistical control can make a huge difference in practice. And then I've argued that you need to have a clearly articulated research question and clearly articulated causal assumptions to justify whether you must or must not control for additional variables, independently from the fact whether it actually makes a difference in the results. So it's a theoretical question first and foremost. I've introduced you to causal graphs, to directed acyclic graphs that visualize causal assumptions. Then we walked through deseparation and to see how specific causal graphs or causal assumptions would imply certain correlations or non-correlations. And then that led us to the backdoor criterion, which I think is pretty easy to understand. given that you have committed yourself to a certain DAG, and given your research question, if you're interested in a simple causal effect, then you can check with the backdoor criterion whether what you need to control for and what you must not control for. And the things you must not control for are, in this context, so-called post-treatment variables. So variables that are influenced by your independent variable of interest. I've shown you how this can be a problem. We'll return to this actually in 5 minutes or so. And then lastly, I showed you how if you still suspect that there is some unobserved confounding, that you can use this really nice SenseMaker package to run a so-called sensitivity analysis to assess, perhaps by benchmarking, how sensitive your estimate is to unobserved confounding that you have not accounted for. So that was the main part of the workshop. I think all of this is incredibly important, and I hope that at least some of you have learned some things about causal inference and what can go wrong and what can not go wrong. There's one more question, Edward. The answer is no, just to quickly answer that. And so for the remaining 45 minutes or so, I'll accelerate quite a bit, I think, and I'll try to talk a bit about causal mediation, which is closely connected to this post-treatment bias phenomenon. And then in the end, perhaps also talk about some issues in instrumental variables, all from a causal graph perspective. So if there aren't any questions on that first big part. Oh, that's a good question. Edward asks which literature you can refer to. I'll send around the slides later, and there's references at the end of the slides, including textbooks and articles, many of which are about DAGs. I cannot really recommend one single textbook for everyone, but perhaps the best is, I'll just quickly write that into the chat. Yeah, that's a pretty good one that is also not that long. It's pretty small, just 150 pages, and discusses quite a bit of what I've also discussed. But unfortunately, I cannot wholeheartedly recommend the one textbook for everyone. Okay, so I don't think there's any more questions. So let's talk about causal mechanisms. Here's a few just quick examples on causal mechanisms from social science mostly. So how does the economy affect what people think and how people vote? How does the incumbency effect work in politics? Do proportional representation systems redistribute more because of different coalition dynamics? Is any given hiring process discriminatory? That is there a direct effect of something like gender or race on the probability to receive a job that does not go through qualifications? Do some genes cause lung cancer only through their effect on smoking behavior? Which is what the tobacco industry used to argue. Does cognitive behavioral therapy only work because it leads people to use antidepressants more often, which would mean you probably shouldn't do the therapy, only use the antidepressants, and so on and so forth. All of these questions are related to direct or indirect effects, or both. And I think everyone should have an intuitive understanding of what a direct or an indirect effect is, also just from everyday life. And so statistically speaking, from a causal inference perspective, historically, people have, for a long time, have estimated direct or have tried to estimate direct and indirect effects using structural equation modeling since the 60s or so. with mixed results, I guess. And the literature really exploded around 20 years ago, where with an article by Pearl, who generalized the concept of a direct and indirect effect to general nonlinear models beyond linear models. And that really kicked off an increased interest in statistics and epidemiology and sociology and other disciplines. And I will actually show you some implementation of this in the mediation package, which was created by Kosuke Imai and co-authors who are political scientists. But this is certainly something that is of relevance to almost every empirical discipline that works with non-experimental data or experimental data for that matter. And so, as I said before, I'll just accelerate and perhaps spark some interest among those who cannot fully follow me. I think you can get a good grasp at direct and indirect effects and a very basic approach how to estimate them by thinking about a linear graph or linear causal model, which is depicted here, where I've indicated by the betas that the causal relationships in this graph are all linear, and it's just one specific beta that indicates how D influences M, M influences Y, and so on and so forth. And then it's hopefully intuitive when you think about linear functions that if this is what is going on, then the direct effect is simply this beta dy here, and the indirect effect would be the product of the effect of D on M and of M on Y, because that is how linear functions work. It's all neat and tidy and simple, and you just multiply stuff along a path. And this is also historically how most people have implemented the analysis using linear regressions. And the first problem that we'll have is that this is, of course, very often unrealistic. And I have another running example for this here, which is a study by Breda and co-authors, which was an experiment where they gave people newspaper articles to read. So that's D, that was randomized. These newspaper articles talked about immigration, portrayed immigration a certain way, negatively, positively, and some other aspects. And then the outcome of interest is whether people basically changed their opinion towards immigration, depending on what kind of newspaper article they read. And one of the more intricate hypotheses was to explore how this information or this framing in the newspaper article impacted on what you think about immigration. And it was suspected that there are at least two mediators, M and N, where M refers to what people think about the costs and benefits of immigration, and N is more like an emotional variable that signifies whether you are anxious about immigration. So these are two different mediators, one of which is kind of more like rational, and the one is more like emotional. And the question is, does this treatment work mostly through one of these, or perhaps through neither of these? Perhaps there's an unexplored channel that in the graph is depicted by this direct effect. So that's the basic setup. And as a first step, let's just simplify this and forget about the one mediator and just concentrate on just one of those mediators called N that simplifies the graph. And that leads to a first estimation strategy. If you just stick to linear regressions, there's a few things you can do. First of all, you can do a regression of the outcome on the randomized treatment. There are no backdoor paths because the treatment is randomized. So there's nothing you must control for. On the other hand, you must not control for the mediator because that would distort the estimate. It's a simple regression of the outcome on the treatment that gives you the average treatment effect or average causal effect or whatever you want to call it. And then the second step would be to say, okay, then you control for n. In an additional regression, you block the indirect effect, you block the path that goes from d to n to y, and that should give you some estimate of the direct effect of the treatment on the outcome. And then there are two options for the indirect effect. One is to subtract the direct effect from the overall effect, which indeed, assuming everything is linear, gives you, assuming this graph is correct, gives you a good estimate of the indirect effect. Or alternatively, you do two more additional regressions of n on d, n of the outcome on n and d, and multiply two regression coefficients, as I've alluded to earlier, and that will also give you an estimate of the indirect effect. And let me just quickly walk you through how that would look like. So here are two regression results. On the left, you just get the average causal effect that tells you that a specific kind of treatment increased opposition to immigration by like 0.44 points. And then the second regression controls for this one mediator here called emo, for emotion or anxiety. And you see that the estimate for the treatment drastically changes. It becomes much smaller and insignificant. So if you believe that all of this is correct, then you would infer that the overall causal effect is positive and kind of large, and significant, whereas the direct effect, you cannot even say it's significant. So perhaps you would stick to the null hypothesis and say it's 0. So overall effect is 0.439, direct effect is 0.161, insignificant. And then one way to calculate the indirect effect is to take the overall effect, subtract the direct effect, and what is left over has got to be the indirect effect, the treatment increasing anxiety, which in turn increases opposition to immigration. And alternatively, you can also regress the mediator on the treatment, which gives you this result, and regress the outcome on treatment and mediator, which gives you an estimate of the mediator effect. You multiply these two things, and this 2 gives you an estimate of the indirect effect, which happens to be exactly the same or approximately the same as with the other estimation strategy. So that's a pretty basic approach that you can choose, but there's a few problems with it. So one, the graphs did not have unobserved confounding. And the question is, okay, what happens if I have unobserved confounding? Does that create problems? Are there maybe even other problems when I'm interested in mediation analysis? Which leads to the second question, can we do some kind of sensitivity analysis, perhaps, if we have to? It's also unclear how to do this for nonlinear models like logit. This strategy that I showed you really relied on linear regressions. And also, it's not immediately clear how to get standard errors for the indirect effects. You just subtract it to things, but it's not super straightforward to then get a standard error for the indirect effect. And all of these problems are basically solved in the mediation package, which you're going to use in a minute, which is really easy to use. And takes care of all of these things on the implementation side. But I want to concentrate a bit more on the conceptual side, on the so-called identification side. So what if there's unobserved confounding? How do we need to think about that? What do we need to control for? Is there anything we must not control for, et cetera, et cetera? Let's discuss that before we go to the implementation. Okay. And for time reasons, I've got to skip something about the general definition of direct and indirect effects, which is kind of intricate. And instead, we'll discuss what do I need to control for, what must I not control for. And now it comes in really handy that we talked about post-treatment variables. And this was also one of the questions from someone earlier that I didn't answer, but I'm going to answer it now. So we talked about this phenomenon in this graph where the treatment, the independent variable D, does not affect the outcome at all. But once we control for this post-treatment variable M, we create a correlation because it's a collider. However, someone asked about this, couldn't we just not control for U too in order to solve this problem? And this is exactly correct. So if we look at this graph from a mediation perspective, then what we would like to have is we would like to correctly infer that there is no direct effect of D on Y that does not go through M. And so the first step certainly would be to control for M, because we think, well, I mean, here not actually, but at least we could think that it is a mediator. But then confounders of that mediator and the outcome also become relevant, not because they have anything to do causally with the independent variable, but because they impact on the mediator that we are interested in and the outcome. And then it's a relatively simple deseparation question. You have one path that you would want to block because it's non-causal. It goes D to M to U to Y. When you control for M, you open up the path because it's a collider. But it turns out that when you control for U, you undo that and you block the path again because U acts as a fork or as a confounder. And so if you ran the regression of the outcome on U and M and D, then the coefficient on D should be 0 because there would be no open path left between D and Y, which is the correct answer if you're interested in the direct effect. And so that is the first problem that you need to solve. So if you are interested in a mediator, you also need to think about confounders of that mediator and the outcome exactly for this reason. Now, unfortunately, there's an additional problem that has nothing to do with unobserved confounders. And for that, we return to the original graph that I showed you in the beginning of this section, which has the two mediators in which are of interest in that actual study. So the two mediators are M and N. And now let's say we are still interested, we still have like N, so this anxiety variable is our mediator of interest, and the M thing is just a thing that is there, but we don't care about it substantively speaking. So let's just concentrate on N. And let's just say we want to estimate a direct effect of the treatment on the outcome that does not go through N. And just to be sure we're all on the same page, the effect that I'm talking about is like this direct effect here that goes from D to Y directly, and also the effect that goes from D to M to Y. So I want to exclude, I want to estimate the effect that is left over that is not going through N, but that includes this arrow and then this path. And then the question is, should I control for M? And that's my question for you guys. And I have a poll. I'll send you the link in a second. And here it. So again, the question is, should you control for M or not. Okay, the votes are coming in. Twenty votes. 27. 30. Okay, I'll share the I'll share the results because they are kind of interesting. So I think some people are still voting, but we have a pretty mixed picture, I would say. So we have a slight majority that says we should control for M. We have around a third that said we must not control for M. And close to a quarter says does not matter, neither works. So that's a pretty mixed picture. And I think I can really understand why any of you would pick these three things. So thanks for voting, and let's walk through what is going on here. So the problem is we are focusing on D and N and Y. And so just as in the previous graph here with the U, this other M variable is a confounder of our mediator of interest and the outcome of interest. And so because of the argument that I just made about this situation, here too, that 100% applies, and it would indicate that we must control for M because M confounds the relationship between N and Y. So even that should especially be clear if you just assume for a second that the arrow from D to M were absent, then M would just be a confounder of N and Y that you clearly need to control for. And so I guess that's why many of you also chose that answer. But on the other hand, I've said what we are interested in is the effect of the treatment on the outcome that does not go through N. And so that consists of two parts. It's like this direct arrow, but it's also the DMY path. And the problem here is once we control for M, we block away part of the effect that we are actually interested in. And so following that logic, which also some of you indicated in the poll, you would definitely not want to control for M because you would control away part of the effect you are interested in. So on the one hand, M is a confounder and we would need to control for it because of this collider phenomenon. On the other hand, it's also on the causal path we are interested in, and so we must not control for it. And so it turns out that there's actually no solution to that dilemma. And the correct response to the poll is actually that neither works, and in fact, nothing works. If this is the situation you have, where it's really simple, it's just 4 observed variables, it's 2 mediators, 1 treatment, 1 outcome. You are just saying, hey, what's the effect that doesn't go through the 1 mediator? It's a perfectly reasonable question, but you cannot answer it because you have this unfortunate other so-called post-treatment confounder, which on the one hand confounds the mediator of interest and the outcome, but on the other hand also lies on the causal path or on one causal path of interest. And no matter whether you do control for it or you don't, the answer is going to be wrong one way or another. And that, I think, is a very counterintuitive result because it has nothing to do with unobserved confounding. Everything relevant here is observed. And is something that is very specific to mediation analysis. So perhaps there's a question on that because it's perhaps not intuitive. Okay, yeah. Ofa asks, what happens if you control for M and N and then calculate only the direct effect going from D to Y? Yeah, that is something that you can definitely do. Then in essence, you would treat M and N as just one mediator altogether. And you could actually simplify the graph and just have one mediator that includes the two and just do a standard analysis like I showed you 5 minutes ago. Yeah, and then Ofer has like an intuition that you could like puzzle everything together, which actually does work in linear models if you just stick completely to linear models. But if you don't, and you probably shouldn't, then this actually does not work. And it's kind of complicated to show that, but the graphical explanation is that M has this double role, where on the one hand you would want to control for it, on the other hand you must not, and that's not something you can solve unless you make stronger assumptions or use linear regressions or something like that. Any other questions? Okay, so that discussion can be summarized in something that is like the Backdoor criterion, but is a bit more complicated, that tells you what you need to control for. And it's called the graphical version of sequential ignorability due to PERC 2014. And it says, if you're interested in certain direct and indirect effects with respect to a certain mediator N and a treatment D, then in essence, the important thing here is you need to control for confounders of the treatment and the outcome, as usual, of the treatment and the mediator, and also for confounders of the mediator and the outcome. Plus, none of your control variables must be influenced by the treatment. And that is exactly the problem that we just encountered. The M variable acts as a confounder, but we cannot control for it because it's also influenced by the treatment. It's a post-treatment confounder. And so that here is an encompassing rule that tells you what you need to look at if you're interested in causal mediation. Okay. So that was quickly everything, almost everything I wanted to say about identification. So you need to think about, in mediation analysis, you need to think about confounders also with respect to the mediator, because of like collider phenomena. And you have this additional problem of post-treatment confounding, which you cannot solve without making some stronger assumptions. And so I also want to quickly talk about implementation. So how would you proceed if you think that you can effectively control for confounding? And then the second step, how you can account for unobserved confounding. And you have hopefully already installed the package. It's called Mediation. And the general mechanic is very simple. You just fit two regression models, one where Y is the outcome and D and M are independent variables, plus perhaps some control variables. So that is usually called the outcome model because it's a regression for the outcome as a function of all other variables, including the mediator. And then you fit a second regression, which is called the mediator model, where the mediator is the outcome. And you include the independent variable plus controls. And then it's just one additional command that automatically calculates the total effect, the overall effect, and the direct and indirect effect for many, many different models that you can choose, including logic and others. And now this is what the code looks like in abstract. So here I start with the mediator model, which could just be a linear regression of the mediator and the treatment. Then you have the outcome model, which is perhaps just a linear regression of the outcome on independent variable and mediator. That's the first step. And then you use the mediate function where you name the mediator model and the outcome model. You declare what the independent variable, the treatment, is called. Here it's called D. And then you also declare what the mediator is called. Here it's called M. Then you should save that in another object, which you can plot and summarize. And so what I would ask you now is to do that in Colab. And most of the code is already there. Actually, all of the code is already there. And you can just run it, take a minute, and look at the results. And then we'll talk about how you would interpret the results. And you only need to run the first two sections because the third one is a sensitivity analysis. So we'll do that after the basic stuff. So I guess that worked fast, I hope. So, oh yeah, let me show it how it looks in my Colab. Here we go. So the first bit just loads the package, loads the data set, which is from this experiment by Breda, all that I talked about, does some manipulations. Then this here estimates the simple average causal effect of the treatment. And you see, this was also on the slides, the treatment increases opposition to immigration by like 0.43 points on a 1 to 4 scale, I believe. And then the second part of the code fits a mediator model, where, as you've seen before on the slides, the mediator is called emo, for like emotion, as a function of treatment. The outcome model is immigration attitudes as a function of the mediator and the treatment. And then you use the mediation package using the mediate function to create the analysis. And then you get a table and a plot, if you plot it. Perhaps let's start with the plot. Perhaps I could also zoom in. The plot depicts point estimates and confidence intervals. So the circles are point estimates. The lines are 95% confidence intervals. And you can see that the package estimates that the total overall effect is around 0.43. That's the point estimate, which is also what we estimated by hand earlier here. So that's the total effect. And then you see that the direct effect is smaller and insignificant, which you also saw earlier on the slides. And then additionally, you get the ACME, which is abbreviation for average causal mediation effect. That's the indirect effect. which is about 0.3 and significant. So one conclusion here would be that the total effect is significantly different from 0 and positive. The indirect effect is significantly different from positive. And then perhaps what is useful from the table here above is it also displays the proportion mediated, which is simply the indirect effect divided by the total effect. And so you would say that 63% of the overall effect runs through the mediator anxiety. So that's quite a lot. And so if we believe this exercise, it would seem that this mediator is quite important and mediates much of the overall effect that we see. Are there any questions on the basic implementation? Okay, then I think the very last thing that I'll talk about is how to use a sensitivity analysis for this basic mediation analysis, where we would think that in this study, but also more generally, there are possibly post-treatment confounders, as I mentioned before, and we're just completely ignore that for now. And we're just concentrate on unobserved confounders that influence our mediator of interest and our outcome of interest. So here in the graph, that would be the U influencing on N and Y. And again, if you somehow controlled for N in some kind of regression, what happens is that you block the path from D to Y, which is good if you are interested in the direct effect. But on the other hand, it's also a collider between D and U. So, and you open up the path D, N, U, Y, which creates a non-causal association. And the sensitivity analysis in the mediation package allows us to assess how sensitive our estimates of the direct and the indirect effect are to some unobserved confounder behaving just like this. And so just take a second and go to Colab again. And the code is already there. An abstract that looks like this. The function is called medsense, as in mediation sensitivity. You take a mediation object that you've created before. You store everything in a new object, which you can then summarize and plot in different ways. So just take a second and run that code in Colab that already has that. And then you get results and summaries. And that may take a while. Yeah, and it takes a while because it relies on the bootstrap to estimate standard errors. So it resamples the data and fits, in this case, like 10,000 models, which I think, yeah, you may probably, oh no, the results come in. So it just takes a few seconds and then you get the results. And the most interesting thing are the plots, which I'll also show you on the slides. So, yeah. So the plots are very similar to the sensitivity plots we've already seen before. Here's the first one. That's the one where you plot this object and you have an additional argument that indicates that you want to have it in terms of R squared. So this, again, is very similar to the SenseMaker output. In the bottom left corner would be our original estimate if the confounder would not impact on M or the mediator or on Y, which unfortunately here is not shown in the plot, but you can just imagine that it's there. And then the plot again gives you lines that indicate how large the estimate would be if you had such an unobserved confounder of the mediator and the outcome. And here you see that it seems that in this case, it's the ACME is plotted, so the indirect effect, the average causal mediation effect. And this seems to be fairly robust to strong confounders. The solid black line indicates the 0. Remember that the naive estimate is like 0.28. And only, it seems like a pretty strong confounder, unobserved, of the mediator and the outcome would bring the estimate to 0. So for example, the confounder would need to explain 70% of the variance in the mediator, and at the same time, 40% of the variance in the outcome, which certainly seems fairly strong. So the basic interpretation is just like in the SenseMaker package. Unfortunately, you cannot do this nice benchmarking thing in this package. That is simply not supported. So you have to rely more on your intuition about how large these R² values would be. And then an alternative to this plot, which results if you just use the basic plot function with the object, looks like this, which has not 2 sensitivity parameters, but just 1, which is on the x-axis. It's called rho. And that sensitivity parameter kind of summarizes the 2 R². And it's a correlation, and any correlation can go from -1 to 1. And the correlation summarizes the correlation that is created between the mediator and the outcome that and goes through the unobserved confounder. So you can kind of think of it as if you multiplied those 2 R² values, then you kind of would get the rho. And in the middle is the original estimate. That's it's the solid line. The shaded area are confidence intervals created by the bootstrap. The original estimate, as you may be able to see, is like 0.28, and it's significantly different from 0. And then if that rho parameter increased in value and would become more positive, around 0.5 here, the estimate would become insignificant because it would the confidence interval would overlap with the 0 line. And so you would need to have an unobserved confounder that created a pretty strong correlation of 0.5 between mediator and outcome. So it would also need to positively influence M and Y because it's a positive correlation, and then it would become insignificant. On the other hand, we also see that any confounder that in essence creates a negative correlation, so a negative rho, would actually mean that the true estimate would be even larger than thought, because such an unobserved confounder would make the estimate of the indirect effect smaller than it actually is due to omitted variables / collider bias. And this is on the left side of the plot. Are there any questions on the mediation package and implementation and the sensitivity analysis? Johannes has a good question. He says the sensitivity methods and packages are rather new. And yes, they are. So the SenseMaker package is just like 1 year old. Are they bulletproof, or is there any major critic or criticism regarding them? Well, as usual in science, I guess nothing is bulletproof until you shot the bullet and checked it. The mediation package now is 10 years old and is really well developed as far as I can tell. So that at least with standard models like linear regressions and logits, etc., It's pretty good, and I've never encountered problems with it. You may encounter some problems the more exotic your models become. If it's like a negative binomial multi-level model, then I don't know. Perhaps at the very least, it could just take very long to compute everything. That is something to be prepared for. The SenseMaker package is younger, but Carlos Cinelli is an amazing scholar, and he's very intelligent, and I think it's a great implementation. So I'm reasonably confident that that package too is very solid. And with that, the only problem I've ever encountered is sometimes the plots are a bit off, like the labels, but that's minor. So both are great. So both the mediation package and the SenseMaker package are great packages, I think. And I've said it before, the SenseMaker thing is something that you should probably use in almost every study that you do, because it's such a common problem on observed confounding, and the implementation is so neat and tidy. And then there's perhaps a closing comment by Edward, who writes that, what about the DAGs and deseparation? Somehow it has been a shock to me, having been educated with the orthodox approach. Is there a huge academic debate surrounding them? That's a really nice question. And because we just have a few minutes left, I'll answer that in a minute. I'll skip a few things about instrumental variables because we don't have time, because you had so many interesting and good questions. So that's a good thing, I guess. So let me just quickly conclude everything, and you'll get the slides later anyways. And maybe I was just too ambitious. So thank you again for your participation already. I was really unsure how interactive this whole thing would be. And of course, it was only me who did the talking, but thanks to everyone who wrote into the chat, also on YouTube, and who participated in the polls. And I hope everyone could at least learn something. I think we've covered quite a bit. Really, the important basics of causal graphs. If you know deseparation, you can more or less follow a lot of the recent research too in that area. I think backdoor criterion, post-treatment bias are very important topics for every empirical scientist. As I just said, the SenseMaker package is something I can really recommend. And I hope that I also alerted you to some problems in mediation analysis. And to answer Edward's question about DAGs and whether there's an academic debate surrounding them, yes, there are. So it took a pretty long time. It's still an ongoing process of DAGs being accepted into various disciplines. And some disciplines are more open to them than others. But I think the trend is extremely clear. And there are, I think in statistics and artificial intelligence, there are one standard tool nowadays that everyone has to know more or less. And so I think they're here to stay. There's a few things you can criticize about them. Sometimes it's easy to draw like a simple graph that maybe is too simple for most realistic scenarios. But on net, I would say it definitely pays off to look into that and to try to learn some of the stuff about it. As I said before, if you look at the slides at the end, there's lots of material, both articles and books. This one here by Pearl Causal is a big book. I've already mentioned the Pearl Glimmer Jewel Primer, which is a neat small textbook that may be of interest to some. And so let me conclude by again saying thank you. I'll stay online, I guess, to answer more questions. And I hope to see everyone in person at some time, somehow. So thank you very much and take care and goodbye.